I should begin with an explanation. A few days ago, I had a virus, and it paralyzed the left-hand side of my face. So that if it doesn't seem quite the shape you expect, please don't adjust your sets. It will go away in a few weeks, I'm told, but be aware that I'm not at my best. I want to talk to you about light. You all know what light is. Life would be pretty hard without it, because it's our chief means of communicating with the world. Most of the information you receive about the world comes by light through your eyes. So much so that in the English language, when you want to say that you understand something, you very often say, I see. And so light, electromagnetism if you like, is one of the earliest topics into which people researched. And so you might find it surprising that after all these centuries, not to say millennia, of trying to understand light, that there is more to do. But I hope to convince you today that there is indeed much more to do. Some of it we're doing here at Imperial College. So this was an early attempt to see how to control light. Many of you, particularly those of you who've read physics, will know about Snell's law. And Snell's law is the law which tells you how light behaves when it meets the medium of a different refractive index, light on glass or light on water. Actually, if I were lecturing to a French audience, I would call it Descartes' law, because Descartes invented it more or less the same time. And Newton has it in his Principia Optica without acknowledgement. Well, we all know about Newton, don't we? Now, this man didn't invent the telescope, but he made a damn sight better telescope than anybody else. By the way, I wonder how many people know that this object here, which we call a lens, that its name comes from lentil, the bean, which is popular in the Middle East. And of course, it's lenticular in shape. That's by the way. And I want you to notice that as soon as you want to do something with light, you have to use a material, in this case, glass. And one of the themes of my lecture will be that the number different sorts of material available to you is very limited, and it's one of the things which prevents us from doing more than we might with light. So control of light is vital to using it, and we need materials to exercise that control. But what is light? At the time of Snell's law, people thought of light as a stream of particles. And it was only later that they came to realize that it was, in fact, a wave. And only later still did we realize of what that wave consisted. And the story begins here in London with Michael Faraday, who discovered the laws of electromagnetic induction at the Royal Institution. And Faraday thought about magnetism in a different way from most people. The Newtonian idea of force was action at a distance. So Newton thought of two electrical charges or two planets exerting a force in one another, and the force acted through space at a distance. In between them, in particular the planets, was nothing, vacuum, emptiness. But Faraday's picture was different, and he adopted something called a field. And he said that whether or not magnet A was exercising a force on magnet B, even if magnet B wasn't there, there was something present called a field. And this he called the magnetic field. And he could reveal that by scattering iron filings on a piece of paper, which you put over a magnet. You must have seen this experiment, those of you who are physicists. And the orientation of the iron filings reveal the lines of magnetic force. Now, what Faraday discovered was that if you change these lines of force, for example, if you move this magnet, then that motion, that changing magnetic field, induces an electric field. And so if you put a coil of wire around the magnet and you drop the magnet out of the coil, then you'll see the needle move on this galvanometer here. So the laws of induction were discovered by Michael Faraday. Now, Faraday was a friend of this man, who also worked in London at King's College, James Clerk Maxwell. He was, in my opinion, the greatest British mathematical physicist of the 19th century, a very, very brilliant man who died far too young, and for that reason is probably not as famous as some of his contemporaries. It is said that a photograph of, or a picture of Maxwell sat always above Einstein's fireplace in the Institute for Advanced Studies in Princeton. Such was his hero status to Einstein. Now, these are the only equations I'll show you, but I do have to present these because these are Maxwell's equations, which are a complete description at the classical level of electromagnetism and therefore of light. And this was Maxwell's way of expressing Faraday's law. So he said that if the magnetic field changes with time, and that's what this symbol means, then you get an electric field. But Maxwell also made an absolutely vital contribution to the understanding of electromagnetism by recognizing that as well as a magnetic field changing, producing an electric field, if you change the electric field, then you also get a magnetic field. And this displacement current here was Maxwell's creation, and it completed the laws of electricity and magnetism. And I think it was Kelvin who suggested to Maxwell that these equations had a wave-like solution. Maxwell quickly found these waves, and he calculated their velocity, and that velocity coincided with the known velocity of light. So Maxwell had discovered that light consisted of electric and magnetic fields, one changing into the other, constantly changing into one another. So you can think of light as a dance between electricity and magnetism. The step of the dance is the wavelength, and the beat of the dance is the frequency with which the light oscillates. Now, that was quite a radical concept at the time, because if you go back to Faraday and you think of this expression of the magnetic force as a field acting on a magnet, then at this stage, this concept of a field is rather a philosophical one. You're free to describe it as action as a distance or as a field and then the force produced by the field. It doesn't really matter at that static stage. But now, what Maxwell was saying was that if you take this magnet and you shake it about a bit, these lines of force behave like a skipping rope which you shake, and waves will travel down them. And the waves can go on and on till they're quite remote from the magnet. The field takes on its life of a life of its own. And then there's no doubt what the correct description of force and fields is. It is in terms of a field. But the question that occurred when it was known that light was a wave, what was it a wave in? If we have water waves, it's water waves about. If we have sound waves in air, it's the air that moves. What moves when light goes through the vacuum? And there was great attempts to talk about a medium, a luminiferous ether, and this conflicted with the notion that vacuum is nothingness, emptiness. If you look through 19th century literature and you want to find a description of vacuum, you find the dictionaries exhausting themselves with different terms for nothingness, emptiness, complete absence. So this was the beginning of a story. And actually, there is a link to Schrödinger here, because Maxwell's waves were the first waves in nothing, if you like. And Schrödinger's equation also is a wave in nothing. In fact, if you take the limit of a massless particle, the Klein-Gordon equation, you get Maxwell's equations. And you have to go one step further beyond the wave equation in electromagnetism to find the quantum effects which are only in the fluctuations of light, and about which I shall not speak today. So that was a great philosophical step forward and a revolution at its time. So to control light, we need materials, and we need materials which control both the electric and the magnetic fields. And I've already explained that there's a shortage of such materials in optics, and in fact in electromagnetism generally. And I should explain that once we start talking about electromagnetism, part of the same phenomena as light are the radio signals for your mobile phone, the X-rays you use in a hospital, the terahertz rays which we use at the airport for security. So with ordinary materials, if you want a different property, you usually think of changing the chemical composition. So if you want glass to be more refracting, to make some bright crystal, you'll add lead to it. It makes it brighter. But there's another way of changing the properties. The properties of glass are due to the molecules of glass, and actually the response to the electric field is an average over many billions of atoms which sit inside a wavelength of light. And it turns out that the things which are responding to the electric or magnetic field don't have to be as small as molecules. They can be quite a lot bigger, and you still do this averaging process. And so it is that you could think of structures which were not less than a nanometer in size, but were, say, a few tens of nanometers if you're dealing with visible light, and they'd still behave as though they were molecules. But things that are so big, you can actually manufacture and make yourself. So by adding structure to chemistry, we enormously expand the material properties to which we have access. So here is a very early metamaterial made by Mike Wiltshire, who is now a very senior postdoc in electrical engineering here. He was then at Marconi, where this whole story started. And here he's making something to control radar waves. So radar waves have a few centimeters wavelength, so these little molecules, constraints on their size are much less fierce, and these structures are 5 millimeters across. They're copper rings, and because they're in the shape of a ring, if you put a magnetic field on this structure, you'll get a current flowing around here, and the current gives you a magnetic response. So in this instance, we're producing a material which has a magnetic response, but it's got no intrinsically magnetic stuff inside it. There's no iron or nickel or what have you, just copper. But it's still magnetic. So that's one example of a metamaterial. Here's another one which incorporates some of these so-called split rings. It was made by David Smith, my longtime collaborator, then at UCSD. And this was designed to have a negative refractive index. Turns out this is the recipe for a negative refractive index. I'll talk more about that later in my lecture. But what I want to remark now is that refractive indices which are negative are never found in nature. They just don't exist. And so a whole new field of study, not the only field, but one of the fields opened up by metamaterials, has been this subject of negative refraction. And this was the first negatively refracting structure. If you want to control light and not radar waves, then the costs go up because you have to manufacture things much more finely. And here is a very clever structure called the fishnet structure, for obvious reasons, made by the Jiangsu group at Berkeley, California. And the dimensions here are the order of tens of nanometers. This is about the wavelength of light, so you can see this structure is just about sub-wavelength and qualifies as a metamaterial. So that's what metamaterials are, and it's opened up a whole new field of study in physics and engineering and optics generally, because we can do so many things. We can access many more properties. And rather than give you a great catalogue of metamaterials, I want to tell you about some of the things and some of the exciting ideas which are now enabled by these new materials. But before then, I can't go on without mentioning that we have quite a lot of metamaterials activity here, thanks to the Leverhulme Trust. As Maggie mentioned, they've given us a very substantial amount of funds, and that's enabled us to put together this team of people here, my collaborators in the physics and electrical engineering department who collaborate with me on metamaterials and their development. Let's come back to Maxwell's equations. Now, Snell's laws, all very well, but it doesn't know about the wave nature of light, so it doesn't know about diffraction. It doesn't tell you how much light is reflected at an interface, because in Snell's law, everything goes through that interface. And so really, if we want to be accurate, we have to look at these equations. Now, I challenge even the brightest mathematicians in the audience to stare at these equations and visualize how light might behave from this laser pointer refracting and reflecting around this room. They're not very transparent, are they? You can give them to a computer, it will give you an answer, but then again, you might as well do the experiment. So what we seek is an intuitive understanding, and that, despite its deficiencies, Snell's law gives us brilliantly. We can see in our mind's eye particles streaming through the glass and changing direction as they go. And we can use this as a tool of our imagination to design new structures and see ahead of time, without actually doing any maths, how that structure will behave. And we want something similar for Maxwell's equations. Now, to do that, we're going to turn to things which we can visualize. And we're going back to Faraday and using the field lines, which were Faraday's way of thinking about magnetism and electricity, because Faraday knew very little maths. And all his ideas were put in terms of pictures of fields. But we're going to need some mathematical help. And to do that, we're going to turn to Einstein, and he's going to help us with something which I call transformation optics. So here's the old optics. There's the ray approximation, which essentially assumes that light is a stream of particles. Talks about refraction at discrete interfaces, but it's very visual. And we want a new vision of transformation optics, which works in terms of the electric and magnetic field components of light, and will enable us to go inside the wavelength, where our research increasingly takes us beyond the micron scale of the wavelength into the nanoscale of the nano world. And we want to exploit the potential given to us by metamaterials. So Einstein's, that great fan of James Clerk Maxwell, is going to help us. Because to continue this story of is space really emptiness, nothingness, this is an essential part. So a one-slide tutorial in general relativity. Are you ready? It's going to be rather quick. What Einstein did was to follow this line of fields producing forces, if you like, So Newton thought of gravity as force acting at a distance, a famous 1 upon r squared law, which he announced with a gravitational constant in there. Einstein said, well, what we should really do is to think of gravity creating a field. And in his case, the field was a distortion of space. So in Einstein's view, space wasn't empty, nothingness, devoid of everything. Space was something which had recognizable properties. And the property he homed in on was something called the metric. And in his worldview, a gravitational field changes the metric. So if you squash space, the metric changes, the metric increases. And if you rewrite Maxwell's equations using Einstein's theory of mixed up space, then this quantity he identified as the metric, which tells you how much space is crushed by the gravitational field, the metric appears in Maxwell's equations in the same place as does the refractive index. So it's not surprising that if the sun is crushing space around itself, and as far as light is concerned, that's an increased refractive index, then the sun is going to act like a lens to light. And it was the bending of light by the sun, as measured by Arthur Stanley Eddington in 1919, that revealed the truth of Einstein's theory, the general theory that space had these properties which could be bent by gravity. So the deviation of starlight, very small, by the sun was proof of what Einstein was saying. And that created a huge furore at the time because light is a massless particle. It's not supposed to be bent by gravity, but it is, and Einstein was right. So what we're going to do is to say, well, I want to draw a picture of these fields, and I'm going to use these lines of force which Faraday used. They have no beginning and no end except on charges. Closer together they are, the stronger the field. And the direction of the field line tells you where that field would exert a force on a test charge or a test pole that you put there. And we may want to manipulate these lines of force. We may not want them to be there, or to put them in another place, to concentrate them, to shove them out of a region. And so I'm going to imagine that they're embedded in a rubber space. And if I want to move them, I'm going to pull on that rubber sheet. And if the lines of force are truly attached to that sheet, then as I pull on the rubber, so the lines of force will be moved as well. And I'm going then to appeal to Einstein and recognize that if I squash my space, I'm going to change the refractive index. And so if I go to Einstein, who has a ready-made formula in terms of how these coordinates are distorted, which tells you what the refractive index is in terms of the metric, it's proportional to the metric, then that refractive index will send the field lines in the direction that we want. And so we retain this visual picture of being able to visualize light in terms of entities which our mind can handle, and how they might change if we change the properties of the materials, the metamaterials we're going to use around those objects. So we were quite excited about that. We got the tools, we got the metamaterials. What were we going to do with it? How were we going to show the world that this was something to be excited about? Well, we need a little more than I've told you so far. You're a dedicated audience of physicists, I know, but the readers of The Sun may not be so wowed by metrics and differential equations. So we thought we might attract some attention by saying we could make something invisible. And we did attract a lot of attention. Now, the problem about invisibility is that black is not enough. Conventional stealth is just a pot of black paint black to radar or whatever you're trying to hide from, and you paint your object with that paint, and it doesn't reflect any light. But as you can see, the problem is that if you're in a bright environment, for example, if you play squash with a black ball, and that black ball is perfectly visible because it has a shadow. And so it is with Peter Pan. I'm sure you all know that this is a statue in Kensington Gardens, just north of this site. So the real problem is not making something black, but making the shadow go away. How are we going to do that? Well, this is a trick. We know how to manipulate these lines of force or the rays of light. This law of manipulation applies to electric and magnetic field, and by the way, it applies to the old-fashioned rays as well, so you can think in terms of rays if you want for the present argument. So this is what light would do if we just had an empty space here, and of course if you put an object in this inner region here, the light would bounce off it and you'd see it. So we want the light to avoid some inner region. And at the same time, we don't want to lose the light, because if we did, we'd make a shadow. So what we want to do is to have the light do a kind of chicane, like a skier going around a tree. But after it's done this chicane, it should continue on the same path as it started on before. And I think you can see that this tool of transformation optics is ideally suited to this job. So what I'm going to do is to take this space, this rubber space, I'm going to poke my finger in the middle of it and tear a hole and push space from the center of this sphere into this annulus here. And as I compress that space, I take with it any rays of light that happen to be traveling through that space. So that successfully clears out any ray of light that had any thought of entering this inner region here. So no light gets into this inner region. It's a totally disconnected piece of space. But the really neat bit is that if you don't distort space, you don't move the rays. So I haven't fiddled about with space here, so the rays will travel on totally unaltered trajectories here. It will be as if there was just empty space in here, because the rays outside haven't noticed anything's gone on, because you haven't altered the space in which they move. And so that's our prescription for, oh, by the way, if you like, I promise you no more math, but if you like math, here's a little transformation that just pushes all the space into this region here. And so this is more highly refracting than that. Right, so anyway, back to pictures. The rays of light will now deviate here, but will not be altered here. So if you're an observer here, what you see is what is behind the object and behind the cloak. You'll see neither the cloak nor the hidden object. But we really do need metamaterials here, because what we need to do is to make a continuous gradient of the refractive index. There's a formula for that. We know what we want to do, but doing it requires this additional ingredient of metamaterials to have the flexibility. And by the way, this is an anisotropic medium, and metamaterials are very good at that as well. Now, this continuous bending of light is not something that's totally unfamiliar. If you see a hot road in the summer, then sometimes it will appear wet. And what you're seeing is, in fact, a mirage, where the hot air is being heated by the hot road surface or desert surface underneath. That produces a gradient in density and a gradient in refractive index as well. So light from the sky will be bent, and if the effect's strong enough, it'll be bent right round into your eye, and you see a reflection of the sky in the desert surface. And hence, the thirsty traveler thinks he sees an oasis. Now, this was the first metamaterial cloak put together for radar waves by David Smith's team, who's now at Duke. And here's the gradient of the refractive index as a function of radius. This is put in a two-dimensional radar waveguide. And here's what that first experiment should see if everything was perfect. So here are the rays of radar waves. The cloak grabs them, sends them round, and there's also some waves drawn here as well, if you like the wave picture. This is what you should see if you use the actual parameters of the cloak. It's not a perfect cloak. We had some competitors, so we wanted to do this really quick. So it's not going to be perfect, and this is a computer simulation of what we should see. And here's the experiment. And you can see that, well, you know, it's not Harry Potter by any standards, but it is doing the job of grabbing the waves and sending them, avoiding this object here, and they're coming through reasonably parallel, so you'd see an undistorted object behind the cloak, you'd see through the cloak, but it would look like a grey patch. You'd certainly know this cloak was there, but nevertheless, the principles were demonstrated. And shortly afterwards, I was giving a lecture in the States, and people were waving about copies of the New York Times. I didn't know what it was about until I saw that we'd actually made the front page of the New York Science supplement. So that was an accolade indeed. So that got the attention of people and got them to believe that transformation optics and metamaterials really could do things. If you could do this, you could do anything. But let me now, in the few remaining minutes, talk about some aspects of metamaterials and transformation optics that are going to challenge our understanding and go beyond the ray approximation. So let me remind you that I was speaking of Einstein, and he told that a compression of space looked like an increased refractive index. And you could use his theory to design all sorts of things. But now I mention another name which perhaps isn't famous to you. It's Victor Veselago. And some years ago, Victor wrote a paper in which he said, well, this is ordinary refraction that takes place in water or glass. And in ordinary refraction, in all natural materials, what you find is the light enters this side of the normal, and in the medium, it comes out on the other side of the normal. That's normal refraction. But Victor said there's no reason why you shouldn't have this sort of situation, and then this angle being over here rather than over there means the angle is negative, and if you plug that into Snell's law, that tells you that the refractive index is negative. Now, you might ask, why are you getting worked up? Why are you telling me this? Why are you getting worked up about a number being negative? We know about negative numbers. We even know about imaginary numbers. So why are you getting so excited? It's this connection with space. You can think of a compressed space. What is a bit of negative space? Excuse me, I usually do some origami at this stage of the lecture with my notes. So let me try and explain a little more. What Victor also pointed out was that if you have this negative refraction, this chevron sort of refraction, then bending the light back towards the axis means that you're going to create a focus in here. In fact, you create two foci with a slab of this stuff, one inside and one outside. And you can think of making some negative refractive material by crushing space. So here I've got a bit of space, two-dimensional, it'll do, and I'm going to squash it. And as I squash it, it becomes more refracting. Squash it, and then I really squash it, and it becomes infinitely refracting. And as a mathematician, one can push a bit harder. And if you know about 1 upon x, then 1 upon x as you go through x equals 0 goes from plus infinity to minus infinity. And that's exactly what happens to the refractive index here. So if we push hard enough past this infinite compression point, we get to the stage where this bit of space in the middle has a negative refractive index. But, oh dear, we've done something very unfortunate. We've crumpled space, okay? So space is triple valued here. It's got 3 manifolds to it. So the light, you think the light's going through like this, but what the light thinks it's doing is going forwards, backwards, and forwards, because this bit here is a piece of negative refractive index, a piece of negative space. And therefore, the way that you think of this focusing event, if you follow Einstein and space and so on, is that this point here, this focal point, is passed once, twice, and thrice. And that picture of that event being passed 3 times is not an approximate picture. This picture of transformation optics is exact at the level of Maxwell's equations. And so we draw a rather startling conclusion from this, that this focus here is exact. And so if we have an image here, an object here, let's say, then this image of the object will be perfect. Now, those of you who know about the wave theory of light will know that microscopes do not resolve anything which is smaller than approximately the wavelength of light. And that is a fairly rigid rule of microscopes. But it's only a rigid rule of microscopes as they are currently designed. And if you were able to make a microscope with this negative refractive medium, providing you made it perfectly, you would obtain a perfect focus here. And I pointed that out some 10 years ago. I was roundly criticized for my pointing it out. And there were many battles later, that conclusion is now accepted and will be the basis of making instruments which can gather light on a scale which is far less than the wavelength. So quite a revolution in our way of thinking. So that's another surprising thing that you can do with metamaterials, that you can do with transformation optics, which is not explained in the ray approximation. So another surprising thing about negative refraction is this. So imagine that you could make a liquid with a negative refractive index. Then let's do some ray tracings. An object here will produce an image above the surface. You can understand that quite well because some of you will have done an experiment in school in which you notice that an object in a tank of water appears nearer to the surface than it really is. And actually, you can measure the refractive index like that. You can take the real depth or the apparent depth, and that's the refractive index of the water. Real depth or apparent depth. But if the refractive index is negative, then the apparent depth is negative and above the surface. So the apparent depth of the fish, you wouldn't have to buy any flying fish. All you have to do is to buy some negative refracting fluid, and the fish in the pond will be above the surface here. It's very visible to you. Now, something else which I'm throwing out a series of challenges to you here to see if you're still awake. Another thing you can do is the original Veselago lens was a flat job, and it produced an image exactly the same size as the object. But I can use transformation optics to bend that round into an annulus, and I can make, by bending space, I produce a lens. Now the lens is all the blue stuff here. Anything outside the blue circle is empty space. And if you're interested, here's the formula for the lens. Put it together. And everything inside the green circle is seen from outside as if it were inside the red circle. So this is a magnifying glass, and it's perfect in every respect. So I like to, convenient bottle of water here. You won't be able to see it anyway, but I try and illustrate this with a bottle of water. Better with a bottle of milk, but I didn't think ahead. Have you ever noticed, if you look at a bottle, a glass bottle, that the fluid inside it always seems to go to the edge? You don't see any glass. It's it will be milk right to the edge. And that's quite understandable if you do a bit of ray tracing, because any ray which hits this glass has to go into the water or milk. And therefore, it always looks as though it's water. Now, I want to contrast that situation if the glass was replaced by this negatively refracting medium here now. So what would happen in that case is that the milk would appear out here. We're sort of super milk bottle, make the milk. How does that happen? How does that happen? Let me try, I won't bother putting that back. Let me try and explain how that happens. And I don't think you'll be the wiser after my explanation, but try it. So let's do a bit of ray tracing. Good old ray approximation, Snell's law. So this ray comes in, goes through the negative glass, comes into the milk, goes out. Fine, we see milk. This goes in, negative refraction into the milk, blah, 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 blah. So all these rays we can explain why they see the milk. What about this ray here? This ray sees the milk, but it doesn't touch the milk. So how on earth can this ray, which is remote from any material of the lens, which is entirely inside the blue circle, how can this ray see the milk? And yet it does. So here's on the right is a computer simulation of Maxwell's equation. I think I have an animation of it. Let me try and do my one animation here. So if you have epilepsy, please look away. This is very bad for epilepsy. So what we have here is a computer simulation. All this is empty space. There are some waves coming in from the left, as you can see. And this negatively refracting material grabs these waves, and it stuffs them into this inner bit. And then when it's done with them, it takes them out, and it leads them back into rays again. So I think you can believe me that this green stuff is just a compression of this, and this red thing is just an expansion of what's inside the green thing. So what Maxwell is saying, and Maxwell's right, whereas Snell is not, you do see the big milk bottle, the big picture, if you like. So, okay, now, one last teaser for you. There are many devices in optics which only work in the ray approximation. And if you make them much smaller than the wavelength, or even the same size of the wavelength, they don't work. And one of those things is the shadow. So large objects produce a sharp shadow, but if you make an object which is small as the wavelength of light, it doesn't produce a shadow at all. It produces a lot of wiggly interference fringes behind it, which are full of light. So it doesn't produce a shadow. It has to be big to produce a shadow. So on the other hand, we may, if we're dealing with very long wavelengths, we may want to make a shadow, and we may not have the space to make something big enough to make a really big shadow. So what do? Well, we fake it. We make a lens like this, which can make small objects appear big, and so we have a really tiny shadow in here, something black, and then we magnify it to make it look much bigger than the wavelength of light. And then it should produce a shadow. And my former student, Wei-Sheng Wei, has done a simulation of this. So here we have, this is the magnifying glass, negative. Here's some black stuff in here. Here's empty space outside the blue again, and some waves are coming in from the left. And you can see that solving Maxwell's equations, you get a really, really big shadow. How on earth does it work? Homework question. So I hope I've shown you that this ancient subject of optics, which is so close to the every details of our life, every minute of our waking life, we use light. This ancient subject, which has been studied so long, is still full of puzzles and challenges. And we're working to elucidate those at Imperial College. And my goodness, we're having a good time. I hope you have tonight. Thank you.